All right, there we go. Okay, so we got this definition of a differential. We just defined that, right? But this can be useful to us because if we want to do like engineering type applications, this is a quick and easy way to approximate what the propagated error is going to be, right? If we do something like, here's the example we looked at last time. So let's say we've got some, we'll just take a math function here, but we could extrapolate this into economics things, or we could look at like if we're manufacturing spherical ball bearings or something like that. I mean, if we want to be able to know if we know what our tolerance is in being able to measure one of the variables, we can we can estimate what that's going to propagate into when we calculate like volume, which involves that measurement, right? But whatever the error is, it's going to get compounded and propagated when we use that measurement in a calculation, right, to find another quantity. So here we had the example, let's just say that y equals x squared is the function we're working with. And we're going to say that when x equals 1, dx equals 0.01. Now, so what's that mean? So mathematically, that has limited meaning. But in terms of this application, that's saying if we were to deviate from the measured value of x by up to that much in either direction, what's that going to do to the calculation that we're making for y, right? Because y is equal to x squared, and this is going to be considered to be the error in the measurement of x, right? Okay, so then we can use this idea of a differential to our advantage. We could say this is the value of x, this is the value of dx, that's f of x, right? And we're just going to estimate dy. Okay, so all we have to do then is use this formula, right? So if f of x is x squared, what's f prime of x? Well, 2x, right? Yeah. So then all we'd have to do to find the estimated change in the value of x squared when we incorporate this error is just multiply f prime of x, and x is going to be 1, times dx, which we're taking to be plus or minus 0.01, right? And what we end up getting then is about 0.02, right? One thing we omitted that probably we should put here is a plus or minus, right? Because we don't know if that, dx, in this case, I guess they're implying that dx is positive, but in any real world case, the error measurement would typically be considered to be, if we're measuring like a length or something, it could be that much too great or that much too small. How does that impact our calculation? Not at all. When we multiply this out, we're just going to carry that plus or minus out to our answer, right? So what this tells us is that an error of 1/100th in measuring x, whatever our units are, is going to result in an error of plus or minus 2/100ths in our calculation of x squared. Okay? So let's look at another one.
So where would the calculation of y equals x squared come from in a real life problem?
Well, it'd be, okay, I'll make one up. Let's do, right here, here's the ball bearing. Perfect, let's do this one. Let's look back at, I don't know, did we finish this? I think we're just barely finishing it, or we didn't quite. So let's revisit this one. So with the measured radius of ball bearing is 0.7 inches, okay? So we don't have to figure that, doesn't matter. If the measurement is correct to within 0.01 inches, right, to within 1/100th of an inch, estimate the propagated error in the volume of the ball bearing. So this is where the function comes from. So what's the volume function? Well, 4/3 pi r cubed, right? And so then v prime is what? This is v prime of r.
4 pi r.
That's v of r.
4 pi r squared.
Yeah, good. So then v prime of r is just 4 pi r squared, right? Which is right there, right? And so then we'd say, okay, these aren't f of x's and x's. This is v of r and r, but same deal, right? The actual change in the volume is going to be estimated by the differential dv, right? And what's dv equal to? Well, v prime of r times dr, right? So there's our v prime of r and there's our dr. Well, we'll just plug in values, right? R is this. So that's what goes in right there, there's the measured value for radius. 4 pi times our measured value squared times the error, right? Which we're going to call dr. And we'll attach the plus or minus there because it could be either way, right? And so we end up with then an estimation of our propagated volume to be 0.062, whatever the appropriate units would be for volume. Well, if we measured the radius in inches, then that's going to be cubic inches, right? So we know that we're going to propagate up to plus or minus 0.062 cubic inches of air from that measurement error in radius. Get it? Okay. Here's where we kind of left off, and I don't know if we ever got to finish this sufficiently. Is that good or not? Well, who knows, right? I mean, it's hard to say. It's completely tied to the context of the problem, right? If we're measuring, give you an example. If we're measuring a distance, and let's say we get it to within plus or minus a tenth of an inch, is that good?
Well, then a tenth of an inch that you're measuring, or you measure.
Exactly. What if what we're measuring is 3/10 of an inch? That's our measurement. Then plus or minus a tenth would be enormous error, right? But if we're measuring the width of the room, well, 1/10 of an inch is probably pretty good, right? Because that's a very small percentage of the overall measurement, right? And so in order to really make this a valuable tool, we want to know what's the relative error associated with our propagated error, right? And so we're not so interested in just purely what is dV. We want to know what is the propagated error as in proportion to, or as a fraction of the total volume, right, in this case. So what's that give us, right? That gives us, we could just plug in numbers, but here's where I wanted to show you that there's a much cooler way to do this, and this is, once again, I feel like we just kind of got cut off a little bit at the end. We could just say, well, that's fine, we can calculate dV, there it is, plus or minus 0.062, and then I could go back and calculate the volume that we'd end up with if R were 0.7 inches and divide those two numbers, right? Yeah, that's a lot of calculating though. Instead, why not do a little algebra? All right, and we'll say, start over on this, right? And so we'll say dV is what? Well, we calculated it right there, right? dV in terms of R and dr is 4 pi r squared dr, right? What is V? Well, the formula for V is 4/3 pi r cubed, right? So there's a lot of algebraic cancellation we can do there. And it actually gives us something that mathematically is pretty meaningful. If we cancel the pi's, and we cancel the 4's, and we cancel 2 of the r's, and we do the algebra, what do we end up with? Well, 1/1/3 gives us a 3 on top, right? We get a dr, and then on the bottom we had 1 r left over, right? See that? So you could even look at this. Now, what if we break this into two pieces? Somebody interpret this for me. If I write that as 3 times the quantity dr over r, that's actually pretty meaningful. What does dr over r represent? Say it again. No, that's a dr over just a plain old r. But what does dr mean? That's in the context of our ball bearing problem. What does dr represent?
The change of something.
The
radius of the ball bearing.
That, right? It's going to be the measurement error in radius, right? Measuring radius. So then dr over r must represent what?
Radius.
Okay, good. So we're just comparing the measurement error to the overall measurement, right? So we could say that's the relative error in measurement. Anytime you divide a change in something by the static value, then or by the initial value or the theoretical value, right? Then that's always considered to be a relative quantity, right? And so we could write that as a percentage if we want to, right? And once again, that's going to be either good or bad depending on, look at the last example, 1/10 of an inch is very poor if the overall measurement is 3/10 of an inch, but it's probably pretty good if the measurement is many, many feet, right? What is your dV over V is what this is equal to, right? Let's not forget that. That represents the same idea, but with volume, right? So this is the relative propagated error. You understand what I mean when I say propagated? What does it mean to propagate something?
So what happens after it's done to something, how changes it in the final?
Okay, so some process has occurred and it's been carried forward through some process, right? People propagate by making more people, right? In math, we're talking about the process of calculating a volume here, and so that's how we've taken this initial error, measurement error, and we've propagated into a calculated volume error, right? So what's the 3 telling us then? That's important.
That's constant change.
Yeah, it's kind of telling us, so when we relate the measured error, right, to the propagated error, the propagated error is how many times bigger than the measured error? 3. Yeah, right? So when you do this calculation, whatever your relative error in measurement was, it's going to be tripled by the calculation of volume, right? And so you can see how propagated error can kind of blossom out of control and you can cause problems, right? Sometimes, a lot of times we're going to work backwards. If we're manufacturing these ball bearings, maybe we've got a tolerance on the weight of the ball bearings that we're building, right? Maybe they're going into flywheels or something, and we need to control the weight very carefully. So we're going to get some spec from, let's say we're an OEM manufacturer, so we're manufacturing a part of something that's going to go into a bigger machine. Well, the people that are building the big centrifuges are going to send us a tolerance sheet and say, okay, we're going to buy a million ball bearings, but in order to do that, you got to be able to meet these tolerances, right? And so then we're going to say, okay, well, if those are the tolerances in weight would be proportional to volume, right? And so we've got to have this, there's going to be some certain quantity then attached to this relative error in volume, right? And then we'll say, that's what we got to meet. Well, now let's work backwards and see what does that mean in terms of our relative measurement error we can allow in measuring the ball bearings, right? The radius. You see where I'm going with all this? Okay? So yeah, that's important, right? Okay? We can do some other cool stuff with this. So we can do problems like that, but we can even do, you can impress your friends on the back of a napkin and do a quick calculation and estimate pretty closely some square roots and things. So you'll be able to, in college, you can impress your potential significant others by showing off your math prowess this way. So what if you want to estimate what is, for example, the square root of 24? Okay, you can do this, you can get a pretty easy, accurate estimation of
Is
this.
this how you do it, class?
Sometimes.
Sometimes.
Mhm.
That's why we use calculators.
Okay. So what could we do here? What do you think?
It's close to 5, so it's like.
Okay, it's close to it's close to 5, right? It's 24 is close to 25, which would be a really good value to choose, right? Because square root of 25 we all know.
4.8.
So what's the function that we're doing here to the number?
Or to the,
We're square rooting, aren't we? Right? So we know then we could say, okay, f of x is equal to the square root of x, right? And what we want to really do is we know what the value, think about the logic here, we know what the square root of 25 is, right? So we want to estimate how much that's going to be tweaked if we deviate a little bit from, if 25 deviates a little bit from 25 back to 24, right? So what's the value of c that we're really targeting here?
1.
If we go back to our picture, right, so here's our picture, right? Here's some value where we're going to look at how much the value of the function deviates when the value of the input variable deviates by dx, right? So if we're trying to estimate the square root of 24, wouldn't we want to say, okay, well let's see how much the functional value of the function is going to change when we go from 25 to, well, we're going the wrong direction, but back to 24, right? We're gonna estimate, what's the estimate in the change of the function, which is a square root function, right? So the square root of x is gonna change how much when x moves from 25 to 24. You get the idea? Okay, so I'm gonna see if you guys can, just see if you can set this up. Take a second and,
Like in our heads?
no, work together and see if you can,
Okay.
see if you can figure out a way that you can make this, well, I'll take a roll. You guys see if you can figure out a way to use differentials to estimate this, okay?
Can you go back to that page with the graph on it and stuff? 'Cause that's kind of,
You don't really need it. All you need, you can, I'll write this up here. You guys tell me the answer though. What's the definition of the differential dy in terms of the function f?
X times dx.
F prime of x dx times dx, okay? Okay, that's all you need.
Okay,
That's
so
all you need. Maybe I'll give you one other hint then. So, here's my other hint. So,
The answer is.
What's dx equal to?
so dx is how much, that's how much you're pushing x away from, right?
So it'd be 1 in this.
It'd be 1 in this case, wouldn't it? Well, actually, it'd be negative 1 in this case, right?
Oh,
so that's,
That's
yeah.
prime of x is.
all right, boys, the ones you have to do, so that's
Okay.
just one half and the negative one half. So it's.
One of you guys should be in charge of taping. That's not in my wheelhouse, keeping those things organized. Isn't this a cool little trick? I love this trick.
My vote.
What is it?
80.7.
No.
It's gotta be bigger than
Yeah.
81. Oh, shit.
This is recording,
82.8.
FYI.
Oh, crap. So if I got 80.7. So then 81.3 then.
I'm not saying.
Oh, I see. Negative. Look at this, that you get 81.3. I got it. Did you get 82?
That's right.
2.81.
2.8.
0.81,
I see where you get, so
82.8.
delta x would be positive. Then
Yes.
because it goes up, so,
Yep.
okay. But it was negative.
Did everybody get 82.1?
82.
I thought you said the square root of 9.1.
Yeah, 80.
So then I just tried to
80.
quickly reverse engineer what I did.
80.3. 80 point whatever, 80.7.
So the correct answer is 82.81. What was ours?
82.8.
82.8. So how did we get it? Let's go through it.
Oh, I got it.
I just love this trick. It's so simple and it's so accurate.
Finally have someone to share it with.
Yeah. Right, so if f of x, we want to estimate, right? We're just saying what is 9.1 squared is approximately what? So what's our function?
So,
So what's f prime? What's c? What's dx?
Oh, I use 16.
0.1.
0.1.
Just kidding.
so
Right.
good question.
So then,
0.1, because we went down.
but this, last time, we went from 25 to 24.
Yeah.
This time we're
Oh,
going
no,
from
oh,
9 to
so
9.1.
yeah,
right?
that makes more sense.
Okay, so then we know that y is always approximated by f of c plus dy every time, right? So what's f of c?
81
81,
plus.
right? That's the convenient value, right?
18 times.
Plus, dx, so it's gonna be 0.1 times f prime of c. Well, 2 times 9, right, is 18.
So in this
And then you
instance.
just switch
So
the
it's,
rest.
yeah, it's 81 plus 1.8, 82.8.
Wouldn't
Okay,
it be just easy to just multiply 9.1 times 9.1?
well, okay, it would, but, okay, but do,
Mental math.
we could do like, I mean, so square roots, you can't do that as easily.
Yeah.
Right? Or what if we were taking something to like the 1.3 power,
Yeah.
okay, so
So yeah.
it's,
Sounds like